In this module, we want to see how to go from the acceleration to the velocity and the position. And we'll look at this in a couple modules, and this is the first. So up to this point, we've had two sort of fundamental relationships so far. The velocity is the derivative of the position, or the trajectory, as we call it, or the acceleration, and the acceleration is the derivative of the velocity. And so if we have the position or the trajectory, we can find the velocity and acceleration as a function of time. The problem is that's not usually the case. We'll usually start with the acceleration, and what we want is the trajectory. So how do we go backwards? Well, in this case, how do we find the trajectory if what we know is the acceleration? And so that's easy enough. We have to then turn around our fundamental definitions. Because the velocity is the derivative of the position, then we say the position is the antiderivative of velocity. So just like before, finding velocity and acceleration given the position was an exercise in practicing your differentiation. Finding position if you're given the velocity is just a practice of your calculus finding antiderivatives. So let's do a simple example. In one dimension, let's say the x component of the velocity as a function of time is given by 5t squared plus 3t minus 1. So if I want to find the antiderivative of this, I need to find the antiderivative of each of these polynomials, and hopefully you've done that before in calculus. So the antiderivative of 5t squared is 5/3 t cubed, and 3t is plus 3/2 t squared, and 1 then is just t. And then we have to add to our antiderivative this constant we call an integration constant, or sometimes just referred to as an arbitrary constant, because it can be any number that's not dependent on time, t. And so we can always check this, that we've done this right, because how we define an antiderivative is just that once you take the derivative of it, you get the original expression. And so differentiate this, the 3 comes down, cancels the 3, 5t squared, that's there. Yep, that's it. And this, the 2 comes down, you get 3t, and then the derivative of t is 1. Okay, and then of course that's why you have to add on this constant, is because the derivative of any constant is 0, so that's a degree of freedom you have in the antiderivative given an initial expression. And so one important key is, if you've done this sort of thing in calculus before, this C is often called arbitrary, and what they mean by arbitrary is it can be any real number, but it is not arbitrary in the sense that it can be anything. It has real physical meaning. This integration constant is not arbitrary in the sense that it can be anything. It has, given a physical problem, it has physical meaning. It's arbitrary in the sense that it's mathematically arbitrary, but for any given example, it has meaning. So if it's not arbitrary, if it has a actual physical meaning, how do we find it? It is determined, this is the key point, determined by the initial conditions. And so we'll do an example of that. We'll describe what that means. It's also, depending on how complicated these get, may refer to it as determined by boundary conditions, but in this case our variable is time, so we refer to it as determined by our initial conditions. Well, what does that mean? Well, our initial position, which we've dealt with before, we like to give it a special name because it has special significance, our initial position, is in fact the trajectory at t is equal to 0. That's what we mean by initial position. Well, if we evaluate our trajectory at t is equal to 0, you put 0, all these terms are 0, we end up with c, this constant at the end of our antiderivative. Therefore, this constant is not arbitrary, it is the initial position. And so that's how we found out what c is. And so our final answer then is 5/3 t cubed plus 3/2 t squared minus t plus x naught, our initial position. Okay, I do want to make one important point. It is not true that this arbitrary constant is always the initial position. The arbitrary constant is determined by the initial conditions, in this case, the initial position. So let's look at an example where you determine what this constant is, but it's not the initial position. So let's say we have our velocity as a function of time is exponentially decaying. It's not a polynomial. It's 10 e to the minus 2t. And sometimes, if it's not important, I'm skipping the units, but we have velocity. We know that this is in units of meters per second. So if I want to know the position, I have to do the antiderivative of an exponential. And I know what that is, and so that's minus 10 over 2 e to the minus 2t. Is that right? If I differentiate this, e to the minus 2t is simply e to the minus 2t times the derivative of this, which is minus 2, so that brings a minus 2 down here. It cancels the minus and the 2 in the denominator, and I get this back. Okay, so that's the antiderivative plus this integration constant c. So I want to do the same thing I did before. I know that the initial position, x naught, is equal to the position at t is equal to 0. So if I plug t is equal to 0 into this, I get e to the 0, which is 1. So at t is equal to 0, the trajectory is minus 5, negative 10 over 2, plus my integration constant c. So solving for c, I get my initial position plus 5. So here I can solve for my integration constant. It isn't the initial position. In this case, it's the initial position plus 5. So my final trajectory, x of t, is minus 5 e to the minus 2t plus 5 plus x naught. All right. So that's practice a couple ways of using antiderivatives to go from the velocity to the position in one dimension. So let's take a moment to look at doing this as vectors. Doing it in vectors is not really more complicated. It's just there's a lot of notation that you have to keep straight. So let's look at a random vector. Velocity. I'm going to have an x component of the velocity, which is a function of time, I hat, and some y component, which is a function of time. I'm bored with polynomials. I'm going to give myself a trig function this time. 2 times sine of 2 pi times time. j hat. So while this is the x is a function of time, the x component of the velocity, and here's the y component of velocity as a function of time. I left my vector as a function of time. I put that in there, right? And so let's say that our initial condition of our trajectory r is equal to 1 I hat plus 0 j hat. So there's my initial position. Here's my velocity. So how do I go about finding my trajectory? Well, what I do is I simply find the antiderivative of the x component of the velocity is the x component of the position, and the antiderivative of the y component of the velocity is the y component of the position. So I just have to do everything more. So let's do x sub t first. Again, now I have to find the antiderivative of this polynomial, and so that's 2t cubed plus 5t plus some integration constant I'll call c1 because I might have another one over here. So for y of t, my antiderivative, so the antiderivative of sine of x, if I take what do I have to differentiate that will give me sine of x? Well, that's minus cosine of x, and in this case x is 2 pi t. But again, if I differentiate this, I'm going to get the chain rule. There's this 2 out here. I get this chain rule that would give me another factor of 2 pi. So for the antiderivative, I have to multiply this by 1 over 2 pi. And this gives me negative 1 over pi cosine 2 pi t. So this is now the antiderivative, and I check this because I can differentiate this, use the chain rule, and I'll recover back 2, and I'll recover 2 sine of 2 pi t. Okay, plus, I can't forget, my integration constant c2. Okay, so now I know that from here, the x component, here's x naught, of my initial condition gives me my initial positions x naught and y naught, which is x at t is equal to 0 and y at t is equal to 0. So now we can do that. X naught is x at equal to 0. And if I plug that into here, the t's, these are 0, and I just get c1, then is my initial x position. For y naught, which is equal to y at t is equal to 0. So if I put in t is equal to 0, I get cosine of 0, which is 1. So that's negative 1 over pi plus c2. Therefore, and this is equal to y naught, which is 0. And over here, the x naught is equal to 1 because I was given that up here. And so the y component at t is equal to 0 is 0. So I can solve for c2, which is equal to 1 over pi. Now I can plug these back into my equations for c1 and c2, and I have the vector form of the trajectory plus 5t plus 1, it's in meters, I hat, plus, have this 1 over pi, I can factor out 1 over pi, 1 minus cosine 2 pi t, meters j hat. Once I put 1 over pi into here, I can factor out this 1 over pi, and I get 1 for this term minus cosine 2 pi t. So Doing vectors, the antiderivatives, is not harder, it's just longer. And the key is that you have to keep separate the x component from the y component. Now we'll look at acceleration then in the next module.